It's like Christmas Eve, Christmas.
Right. So let's see now how we can calculate this in a quantum computer instead. So this boils down to two steps, just sort of like the classical algorithm. First, we need to compute this kernel matrix, and then we need to solve this linear system of equations. So, first, calculating these dot products.
That's assuming you have a linear kernel, or
Yes, this is assuming now that I have a linear kernel. I'm not sure actually how this works if you have a kernel function, but I think you could do something similar still. So the way this is done is by rewriting this dot product in terms of the lengths of the individual vectors and the distance between them. Now we assume sort of that we know these individual lengths. We define Z as the sum of the square of the length, because we need that for normalization later, so it's convenient. Then we construct two states. We construct psi, which is 1 over square root 2, 0, xi plus 1 xj. Now these hexes here with the vectors in them, these are vectors that we've encoded in this using this quantum random access memory. So it's some amplitude encoding where each element in xi becomes an amplitude in front of a basis state. So already here we see that the algorithm that we're going to do, it requires that we have this quantum random access memory, and that it's efficient, which still is an open question whether we can do that. Then we construct a second state, phi, and that is 1 over square root of z times xi kept 0 plus length xj kept 1. Now, with these states, we do what's called a swap test. So what's a swap test? Anyone know? So it's the following circuit. This is the, so you start, you prepare some state, okay, you could start in 0 and do a header mark, you get this plus state. Then you do a controlled swap on these two states A and B. These are the ones you want to do the test on. So this control swap or threading gate. Then you do a header mark on the first qubit and you measure. Now, if you write out the end result of this circuit before the measurement, state is 1/2 times 0 A B plus B A.
Isn't it 0 AB, 1 BA?
One moment.
Yeah.
I'll write the whole thing.
Which state vector is this?
This is the state vector that you have at this point after you've done all the operations.
Okay.
Then you agree?
Yes, I forgot about the header mark.
Yeah, so you've done the header mark here
Yes.
at the end also, and then you rearrange the terms to 0 and 1. So what you can notice here is, here you have plus sign, here you have minus sign. This can be 0 if A equals B. So if A equals B, measurement will always give 0. As a result. If A doesn't equal B, then the probability of measuring 1 will depend on how equal A and B are. This is a way to test how close A and B are. So what you do here is you do this swap test. On the ancilla in these two states. Or rather, I mean, the psi is contracted by an ancilla and then the state, which is the vectors, and then the psi is just this one qubit. So you're comparing the state of psi with the state of that ancilla. And then from this, you will get this distance xi minus xj squared by the fact that you know z, so you know the length of the individual vectors, and the probability of measuring one with this soft test. One. Yes.
Could you remember what ancilla is?
Ancilla is so an additional qubit. It's a term that's quite common in quantum information. I think some people don't like it being used at all because it has some connotations to slavery, some old English word related to slavery. But yes.
But basically, to know accurately the distance, you need to then measure many times, right?
Yes.
And do you then have to re-prepare A and B, or is it some trick where you can sort of just reuse the state after the measurement? Or like, is your quantum RAM, is your sort of your quantum RAM destroyed after each measurement, and you have to re-initiate it?
I'm not sure. What they say is that the complexity for this step is order log n from using the quantum RAM. But then you will have more factors that are not just about the size, but about the precision with which you want to get your result. That also comes in here. But it's not the scaling in n and m. But yes, there is some like order epsilon, or order 1 over epsilon if you want precision epsilon. So this distance calculation algorithm is something that's also used in some other applications, or proposed at least to be used in some other applications. So now we were just talking about the support vector machine. There is this related machine learning problem, or similar machine learning problem of clustering. So if you have unlabeled data, but you want to find sort of, you suspect that it has different groups in it, and you want to find these different groups, then you can look at distance between data points, not to see who are close together, who are far apart. And it's been proposed to use this kind of distance calculation algorithm also for such purposes. K-means clustering. Let's maybe write that. So step 2 then of the quantum algorithm. Okay, so we have now this system of linear equations. Basically, we want to invert this matrix, we call it F. 0, 1, 1, okay. And you can divide this up as 0, 1, 1, 0 plus 0. So they call this J, and this is A prime, let's say. Now, this is, so K here is not sparse, because we have these dot products between each pairs of vectors, then we have as far as I know at least no reason to assume that many of them should be zero. So
Can I just ask, how do I read this? Because K itself is a vector, right? Oh, sorry,
it's a matrix.
A matrix, yes.
So
So there will be zeros on the first row and the first column, and then K there, or what is the notation?
yeah, I think actually these ones are also, these are identity matrices. So this is some.
But is it
here is a matrix.
okay? So is it the bottom right half that's K, and then
Yeah.
there's identity, and zero matrices?
Yes. I don't know if it's exactly the half, but yeah, these are
Yeah.
matrices too.
What I remember, the one there is a vector full of one.
Yes.
The vector is 1, 1, and the other one is like one is a column vector and the other one is the row vector.
Ah, okay.
Okay.
Hmm.
It's just zeros, it's not a block.
So the
So
F
this is an
matrix
actual zero.
yes, this is a scalar, and
Yeah.
the F matrix is one dimension more than K matrix.
Okay.
Okay, yeah, good. Basically, the approach they take here to inverting this F is to find eigenvalues and eigenvectors of it. So they define F hat as this F divided by its trace, which is just the same as the trace of K prime. They want to simulate because this way basically, F hat. This way you can do quantum phase estimation to do the find the eigenvectors and eigenvalues. So yes, J is sparse easy. K is not sparse. And what we want to get at is some, or they use this division to write this as a product as ij delta t, okay, or a trace of k prime times e to the minus I k prime delta t. And then from the fact that we have this QRAM and we've calculated these dot products, you can write down this k hat, k prime hat. And then you're using something that's sometimes called quantum self-analysis. Basically, it's about you have multiple copies of some density matrix draw. And that somehow enables you to perform the time evolution. Now, so in using these tricks, in the end, they can simulate this e to the minus I t. And they use that in quantum phase estimation. Which I guess you encountered in Shor's algorithm. So you can use this to extract eigenvalues and eigenvectors. And you write this y vector which was on the right hand side of this system of linear equations in this eigenbasis. In the end, you have a solution state, the b's and the lambdas. With some normalization. And those is b's and these lambdas that we need in the end. So they say that the complexity of this step is order log of n, similar to HHL. So in total, with that first step of calculating the kernel matrix, you end up with something that's logarithmic in n and m, while we have something polynomial in n and m for the classical algorithm. So you see, yeah, there's quite a few steps and a few tricks, but once you see there is this sort of toolbox for linear algebra. I think we have algorithms here that, like the quantum phase estimation, so lets us get eigenvalues and eigenvectors. We have this distance calculation. It uses that swap test. So we have this toolbox of different quantum algorithms, and they are really bringing it all to bear on this problem. So this, maybe I should say, this is from Lloyd. So there were a number of papers on Lloyd and collaborators in around 2013 where they looked at this and some other machine learning problems. So a few years after they had done that HHL algorithm and sort of had started to see that we have this toolbox of linear algebra quantum algorithms, they were, I think, exploring what they could apply it to. So this is the one we looked at. I know that there is some different quantum support vector machine algorithm which instead uses Grover's algorithm to somehow search for these support vectors faster than the classical calculation could. But then I think the speed up that you could get is just square root of n or m, something like that. And I don't know if that requires the quantum RAM or not to start, just to implement Grover search in the first place. Okay. I think we have time to briefly show one more algorithm. As you see, I can't, there's not really enough time to cover each step in these algorithms in detail, and sort of there are holes here. I'm trying to give the overview of what the different steps are. And I think I promised you last time that we should look at quantum principal component analysis also. Anyone tell me what principal component analysis is? Yeah, that's so you have some high dimensional data. Let's draw a picture like the previous one. Let's say now we have unlabeled data. We have some data looking like this. So there's a variation in the data, but it's not in all dimensions. So we see that there are some dimensions where the data varies more. So you would like to sort of reduce this to just the dimension where you have the largest variations. So in this case, we have some 2D data. We want to reduce it to just some new x prime where it all lies on the line. So we sort of find this line and project on that. So principal component analysis is basically to find the axis along which the data vary the most. And this will then be sort of the axis that are most useful then to do classification. So when you've done this, maybe you do superword vector machine up that where you do some classification along these principal components. These axes of principal components of the data. And now that we've done this, I can state the quantum algorithm very simply here. Or would anyone like to take a guess?
Distance estimation.
Sorry?
Distance estimation.
Distance estimation? What distances would you like to look at?
decide which dimensions I'm cutting down to, and then
So the problem is here how to find which dimension to cut down.
okay.
That's the principal component.
SVD and
Yeah, you can do some single value decomposition. So in this case, they basically do this again diagonalization. So you find eigenvectors and eigenvalues. So you write the data as a matrix. You find the eigenvectors and eigenvalues of the data matrix, and then you see, okay, what are the largest eigenvalues? Those are the ones that they correspond to the components of the data where you have the most variation, that matter the most. So you use this exponentiation and phase estimation like in step 2 previously, basically. And you find the largest eigenvalues. So I got a question in the break here about what are some applications of these algorithms. Like, why would you do this support vector machine, for example? And you can, well, there are many classification tasks that I came to think of was, I've seen there's a data set for breast cancer, for example, where you have images of tumors from mammography, for example, and they are these images, they have a lot of data in them, so you have different x-axis in this data. And you have some labeled examples where you saw that this was benign or malignant tumor. And then you use this labeled data to find hyperplanes so that you can classify new images to make a diagnosis if this tumor is benign or malignant. For this principal component analysis, there are also many uses. The one I like to use when I give some talk about this machine learning to an academic audience is there is a web page called Paperscape. Has anyone seen this? It's going to be fun to have a look. So they basically took all the papers from the archive, all the papers from the archive, and they, for each paper then you have lots of data, like who the authors are, some keywords, the content of these papers. And then they use principal component analysis to break this down into a two-dimensional picture, so you just have variation on two axes, and you plot all the papers along these, using these two axes that you found from the analysis, and you sort of see the different parts of the archive, like astronomy or high energy physics or condensed matter physics. So, and you can see quantum physics also. You can see the connections, and then sort of you see subfields in quantum physics, measurement problem or circuit QED or other things. It's quite fun to explore that map. You can search for like author names and see them highlighted, see sort of where their papers fit on the map. So I recommend having a look at that. It's quite fun. Maybe the cell phone is a bit too small to, if you're trying to find it there. Okay, I think that's it for today. Tomorrow the plan is to look at some quantum neural networks, and then this course will be over. Well, we still have an exam, but we will send out in January. Julia sent out a short questionnaire for the course. I hope you all got an email from her the other day. So I hope you can all take a few minutes to answer the questions there to help us improve the course until next week. All right. Any questions before we begin? Yes.
So what will the format of the exam be? It'll be like a list of a few questions?
A few questions, like sort of like the hand-ins, but a little larger.
Yeah.
And I think we said 1 week for